Well, we've done matrix products and matrix vector products as well. And I mentioned that one of the reasons that we're interested in matrices is for solving simultaneous equations. So here's a pair of simultaneous equations, and I've written it out in matrix notation. So x1 and x2 are the variables, and these are the two equations. And of course it can be written ax equals b, where a is a11, a12, and so on. And you notice that this is possibly the reason for the rather strange definition of matrix multiplication as being a row times a column. And you see that the variables here correspond to the columns in the matrix. Geometrically, these are two equations for lines because they're linear equations in two variables. So if these two lines meet at a point, so the two lines in different directions, not parallel to each other, they'll meet at one point, and that point will be the solution. So we want to be able to write this in matrix form and see if that helps to solve it. Well, to do that, we need the inverse of a matrix. So we say an inverse B exists for matrix A if BA equals the identity. And actually it turns out that if BA equals the identity, then also so does AB. But that's something that we'll check later. So if AX equals B is our system of linear equations, and it could be in lots of variables, but we'd need it to be a square matrix A because we want the same number of equations as variables to be able to solve them. And if we're equipped with a matrix B called an inverse, then we can multiply on both sides by B. And in that case, B times A is the identity, which of course doesn't do anything, and big B times little b is on the right hand side. And so that tells us that x equals big B, little b, and while it is possible that you might have a particular matrix that you can't cancel, in this case, because there's a B times A equals the identity, it is special, it does work. So if this B exists, it's called the inverse of A, and we write it as A to the power minus 1, just as we would in a number. So it doesn't always exist, of course, because two equations in two unknowns might not have any solution if the lines were parallel but didn't intersect. So I could just write the same equation twice, and then it's got lots of solutions. So it's clear that the inverse of a matrix doesn't always exist. So to understand whether matrices have an inverse, we need to look at something called a determinant. Well, geometrically, there's two ways to think of this. One is, for a system of two equations, it measures whether the lines are not parallel. It's measuring obviously something that's related to the angle between the lines. But another way to think of it geometrically is if you get any set in the plane, say a square, and apply the matrix to every point in that square as a position vector, then determinant turns out to be the factor by which the area is changed. So if the determinant's 2, the area is doubled. If determinant's a half, the area's a half. And actually, if the determinant's negative, it means it's also been flipped over, so a left becomes a right-handed thing. So that sounds quite complicated, but it's kind of interesting to visualize. And the point is, if it squashed everything down to something with area 0, you can't undo it. So again, that's a reason why it's important. But it turns out that it's quite simple to work out, and we'll do a 2 by 2 matrix, and we'll call it A, B, C, D as the entries rather than 1, 1, 2, 2, because it's a little bit clearer. And to get a determinant, you multiply A and D, and then you subtract B times C. So you multiply these, A times D minus B times C. And most people just learn that AD minus BC. And we've written the matrix A, B, C, D like that. So if we have an example, here's 2, 3, 1, 4. We get 2 times 4 is 8, minus 3 times 1. So it's 8 minus 3. So the determinant of this is 5. And it's non-singular. It has an inverse. It doesn't squash everything down to 0. For the 3 by 3 matrix, it's a little bit more complicated. And actually, if you've done 1E1 in the first year, you'll know about the vector triple product of 3 vectors. And if you have 3 vectors, and they could be the columns of a matrix, then the vector triple product gives you the signed volume of the parallelepiped spanned by those 3 vectors. So really the 3 by 3 determinant, it's a volume. But I mean, you don't need to know that to work it out. What you need to do is be able to work it out in terms of 2 by 2 determinants. So the conventional way is that we go along the first row of the matrix, and so I get the A11, and then I cross out that row and column, and I'm left with the 2 by 2 matrix, which is A22, 23, 32 and 33. Then next we get the A12, and then we cross out the row and the column that 1, 2 is in, and we're left with this matrix, 2, 1, 2, 3, 3, 1, 3, 3. And then similarly, we get the 1, 3, and then we cross out the row and column. The thing that's tricky and a little bit strange, and possibly the easiest thing to get wrong, is that the middle one has a minus sign. And, okay, that's a little bit odd. And the other thing is, we went along the first row. Actually, you could also go down the column. There's lots of ways of working it out, so this is just a choice. Then to finish it off, we do the determinant of these 2 by 2 matrices. So it's that times that, minus that times that. A22 times A33, minus A32 times 23. So in the end, all the terms in the determinant are 3 things multiplied together, which you kind of expect because it's a volume. But in practice, you sort of probably work these out numerically before you finish. These 2 by 2 submatrices are called minors. So I would actually call this the 1, 1 minor because it's got by crossing out the first row and first column. So the submatrices are called minors. And so it's the determinants of the minors multiplied by the row or indeed column that you're going along. And then there's this weird negative sign to take care of. We also call a determinant with straight lines down the side of a matrix. And in fact, if you just write the square set of numbers with straight lines instead of brackets, that's count for determinant. Strangely, determinants were invented before matrices because they just came out in expressions for solving simultaneous equations. So you even see in very old books on electrical engineering that they knew about determinants but not matrices. Anyway, if you don't put the hooks on the brackets, then it's a determinant rather than a matrix, and that's a number. For example, the 1, 2 minor is the minor that we get from crossing out row 1 and column 2. So that's the determinant of the minor, or sometimes people just say the minor for that smaller determinant. Okay, so remember that weird minus sign in the middle. So as I explain that, actually the sign alternates. So it goes plus, minus, plus, minus, plus. And it's just because it's 3 by 3 that we only notice that the middle one is weird. If we did a 4 by 4 matrix, we'd see it go plus, minus, plus, minus. And so with that in mind, we define the cofactor as plus or minus 1 times a minor. If we take the mij minor, that's the determinant of that submatrix, and then minus 1 to the I plus j, of course that alternates as I either change I or j in a kind of chessboard type pattern. So let's do some examples of cofactors. Here's a general 3 by 3 matrix, and the 1, 2 cofactor I get by crossing out the first row and the second column, leaving me this minor. I work out the determinant of this minor, A21, A33, minus A31, A23. And then I decide whether it's plus or minus, and it's row 1, column 2, so it's minus 1 to 3, which is odd, so I get a minus sign. And of course it just changes odd and even. Similarly, the 2, 3 cofactor I get by crossing out the second row and the third column. 2 plus 3 is odd, so it has a minus sign in front of it. So I can work out all these cofactors. You might have noticed that in my formula for the determinant of the 3 by 3, I didn't have to use all of them, but you can use them all. You can work out the determinant in several different ways using all the cofactors. So there's a formal definition of determinant, which isn't really very useful to use, because in practice you only use this kind of method for either 3 by 3 matrices or matrices that have an awful lot of zeros, so you can ignore parts of them. But this is saying if you fix any j between 1 and n, then you have to add up the aij. This is j is fixed, so we're going along the j index. The aij times the cij, which have the plus or minus sign in. And the fact you can either do that with I or j means that you can either go along a row or a column, and you can use any row or column, which somehow might be, you might just choose an easy one that's got lots of zeros in. So cij is a cofactor. Okay, so that's the definition, not that you kind of really use this. You probably will just remember how to do it for a 3 by 3 matrix. A transpose has the same determinant as A, and that's because we can go along either row or column. So swapping the rows and columns doesn't actually make any difference. A neat fact that's far less obvious is the determinant of A times B is the determinant of A times the determinant of B. And if you think of a matrix doing something to 3 vectors, which changes the volume spanned by those 3 vectors, and then you do another operation, then the change in volume is just a cumulative change of volume. So it kind of makes sense that you multiply the determinants. If D is a diagonal matrix, and it's possible just to check this with a formula, all you get is the product of the diagonals. And of course that makes sense. The diagonal matrix you can think of as stretching each of the axes in each direction by dii, and so the change in volume is a product of those diagonal elements, or we can work it out from the cofactor formula. So let's work out a determinant. Here's a matrix that's it's a 3 by 3 matrix. It has to be square. There isn't a determinant of a non-square matrix, or if you were forced to come up with an answer, you'd have to say it was 0 because it can't be inverted. Anyway, just for fun, let's expand along row 2. I mean, at least it's got a 0 in, which should save as arithmetic. So going along the second row, the first cofactor is determinant of this. 3 times 1 minus 2 times 1, so that's 1, but it's got a minus sign in front of it. Then the 2, 2 cofactor, of course it's changing sign, right? This one goes minus, plus, minus. It's a little bit unfamiliar to go along the middle row. But the cofactor is this 1, 2, 5, 1 got by deleting the middle row and column, the second row and second column. The determinant of that is 1 times 1 minus 2 times 5, so it's 1 minus 10, it's minus 9, and it doesn't change the sign because 2 plus 2 is even. And then finally the 2, 3 cofactor, we delete row 2 and column 3, so it's 1, 3, 5, 1. 1 times 1 minus 3 times 5, 1 minus 15. And of course it's changed, it's gone minus, plus, minus, so we negate that. We get plus 14. And then to get the determinant, we multiply each of these by the elements in the row. So it's 0 times this, which you might have thought well, I didn't actually bother to work out this first one, to save myself some effort. Then it's 4 times the minus 9 and the 1 times the 14. And that adds up to a determinant of minus 22, which means actually that the columns, or indeed the rows, are a left-handed set of vectors if you think about them in that way. That's what the minus sign means. And if you get the parallelepiped spanned by those 3 vectors, then its volume would be 22 in the units of your axes. So a matrix is singular if the determinant is 0. And that kind of naughty matrix is one that we're not going to be able to invert. In a 3 by 3 matrix, it means all the vectors are in the same plane, so they don't span any volume at all. If you write down 3 equations, it means that one of the equations depends on the other 2 at least. So you haven't really got 3 equations and you can't solve them. So what does it mean? So there are some obvious matrices 0. Any row or column is 0, then obviously the volume span those vectors is 0 and you're missing an equation or a variable. If 2 rows are multiples of each other, so you have one row and then the other row is just kind of twice that row, that's just like having a vector and another vector of different length. So it doesn't, it's not independent of the other 3. Or in equations, it's like having one equation, it's just a multiple of the other. So the other thing is that you can have one of the rows or columns is made from a linear combination of the other 2. And that means thinking of either the 3 vectors as the row vectors or column vectors, they lie in the same plane. Again, visually the same thing. And it's easy to check that because, I mean, at least the zeros, because you could expand along that row or column of zeros and you get the determinant 0. It's slightly less obvious, but obviously very useful, how it actually catches if one of the rows was just a combination of the other 2. So looking at this matrix 1, 2, 3, 4, 1, 5, 2, 0, 2, it's not maybe immediately obvious, but column 3 is equal to column 1 plus column 2. So 1 plus 2 is 3, 4 plus 1 is 5, 2 plus 0 is 2. So determinants here, actually funnily enough, it means that it must also apply to the rows, even though you might not immediately spot a relationship between the rows. Isn't that interesting? So it's a nice way of spotting if 3 vectors are in the plane. Just work out a determinant. And so, well, you can expand along any row or column. Choosing one with zeros in just minimises the work because you don't need to work out the cofactor. Okay, so the point of this was to work out the inverse of a 3 by 3, or indeed the inverse of any matrix. So for ordinary numbers, real numbers, any non-zero number has an inverse. And actually that's 1 by 1 matrices, and actually the determinant of a number is itself. It doesn't really mean anything very much. For matrices whose determinant is non-zero, there is an inverse. Okay, so how do we get it? But it's a matrix A inverse, so that A times A inverse equals the identity. And also it will work the other way around. The identity, remember, is just 1s on the main diagonal. Okay, so let's see if we can see anything with an inverse. You could actually work out what the inverse is by solving simultaneous equations by hand in the usual way. But the point about the formula for the inverse of a 2 by 2 matrix is actually, it turns out to be really easy. So here's a matrix 3, 2, 7, 5, and here's another matrix that doesn't on the face of it have much to do with it. But if we check that if we multiply A times B, for example, 3 times 5 plus 2 times minus 7, 15 minus 14, so it's 1. This one is more interesting. 3 times minus 2 plus 2 times 3 equals 0. And you might actually think there's some little trick there that 2, 3 and minus 2, 3 are actually vectors that are perpendicular to each other, so their dot product is 0. And for vectors in two-dimensional space, it's actually easy to cook up a vector that's perpendicular to another one. You just swap them over and change the sign. Similarly, 7, 5 times 5 minus 7 comes to 0, and then the 7 times minus 2 and the 3 times 5 goes minus 14 plus 15. And so we get 1, 0, 0, 1. And part of it is that these vectors were the perpendicular to the other ones. Well, how do we compute the inverse in general? Well, there's a formula, and you don't really use this formula for much bigger than 3 by 3, but it's sometimes nice to know that there is a formula. What you do is, if you write down C, the matrix of cofactors, then and remember that's the minus with the chessboard plus or minus sign, then the inverse turns out to be 1 over determinant times the transpose of the cofactor. It's a kind of weird thing that you have to make the cofactor matrix, and then you have to transpose it and turn it around. So at least in principle you can work that out. For big matrices it gets pretty complicated. I mean, also let's see that, of course, if the determinant is 0, you don't get an inverse. And in fact, in that case, if you do multiply A by C transpose, then you'll get some zeros. Okay, so for the 2 by 2 matrix, we already know that the inverse is AD minus BC. And actually, you could have just worked that out by hand by just saying, give names to the elements of the inverse, work it out and see what they have to be. But the determinant is AD minus BC, and so the matrix is non-singular. So that's good. And then we can go into the cofactor formula. It's a little bit strange because, of course, the minus is just 1 by 1. So, you know, that's det of 3 and det of, it's just 3 and 1. So the only thing that's kind of interesting is this checkerboard minus signs. And, of course, that's plus, that's minus, and that's plus. So it really just, all this is really saying is once you've rearranged them, you just change the signs there and there. So in summary, what we do is we swap the 3 and the 5, and then we minus the 2 and the 1. Because, you know, the cofactor is from deleting the row and column. So the first row and first column, we get 3. We don't have to work out the determinant. It's just a number. And then, similarly, this would go to the other side, but this isn't the inverse yet. We've got to do one more thing, which is transpose it, which doesn't change whether 3 and 5 are, but it swaps the diagonals over. So, I mean, if you notice, the 2 and 1 have got back to the same position that they were in, they've just changed sign. So you can summarize this as swap the sides of these two, swap the signs of these, and then divide by the determinant. And that's the inverse. That's the simple way to get the inverse. People just remember it as swap sides, swap signs, divide by the determinant. So in general, you got A, B, C, D. The determinant is AD minus BC, and you swap the A and the D over, and you minus the B and the C. That's all there is to it. And people tend to remember that rather than, of course, the elaborate cofactor formula. So if we want a 3 by 3 matrix, first of all, we work out determinant. Actually, as you're working out determinant, you end up working out some cofactors as well. So working out the determinant, I'm just going along the first row, 'cause it's just the first thing I come across, the 1, minus 1, 2. And then I work out determinant and it comes out as 6. 6 is not 0, that's all I need. And then I work out the matrix of cofactors. Notice the minus signs here in the chessboard style, plus, minus, plus, minus, plus, minus. You work out all the minors, and of course we did some of them already for working out determinant. And then the determinant, the inverse is 1 of the determinant times the transpose of the matrix of cofactors. So notice how the minus 5 and 3 are swapped over. Once you've got that matrix, it's a good idea to check that it actually works, because there's lots of things you can make a mistake with, and you'll actually catch your mistake if you multiply A inverse, your supposed inverse, times A, and if one of these numbers is wrong, then you can catch your mistake.